Hi class, welcome to lesson 59B. Because I am proctoring an AP exam, today your classwork will also be done as your homework. I will collect your notes as classwork on Monday. Make sure you complete this homework today. Here we are going to review Voltaic cells. Just like in lesson 59, by the end of this video, you should be able to identify and explain the processes involved in operating a voltaic cell. You must be sure that you are able to define and identify the anode and cathode, determine the direction of electrons' flow, explain the purpose of the salt bridge, and explain the energy transfer that occurs during a voltaic cell's operation. I'll start by showing you 4 examples. Then I'll see if I can get the process really stuck in your head. I'll show you a very special music video. Let's go.
Hi friends, this is our friend Sophie and she's going to show us how to read a voltaic cell. Let's take a minute to look at the cell. This is the cell we have. And the first thing we want to do is find how the electrons flow. How are we going to do that?
We're going to use table J and we're going to see where lead and
Copper
are, and copper is here and lead is here, and it flows from the top to the bottom, so then the flow here is going to go like that.
Perfect. So let's go and take this pen and draw arrows across the wire so we don't forget which way the electrons are moving. Okay, now the next step is to identify the anode and the cathode. How do we do that?
The anode is always where it starts.
And how about the cathode?
The cathode is always where it goes to.
Perfect. And the next step is we have to write the half reaction. So what's the half reaction that's happening in this beaker right here with the lead?
With the lead, the lead, since the electrons are going to leave and go up here, it's going to become lead with a positive 2 charge, and it's going to become part of the solution. So
could you write the half reaction right there?
So it's going to go
Okay. That's perfect. So this is oxidation, so we know the anode is oxidation, and ox. Okay, so how about the half reaction for the cathode?
The half reaction for the cathode, it's going to go from the charge to the one not charged, so it's going to go
So how do you know which charge, what's the order of the charges? You're right. How did you know that?
I know that because the electrons are going from here over to here, and so when this gives 2 electrons, it becomes positive because it loses electrons. So then this gains 2 electrons, making it neutral again.
Oh, perfect. So the last thing we want to do is looking at the skeleton reaction, we need to balance it. So what would we do to balance it?
Because it's already balanced, because the coefficient is 1, like, you can just put 1s in front of it.
Okay, so how can you tell it's balanced from the half reactions? What in the half reactions tells us it's already balanced?
Oh, the electrons, sorry.
So no, it's okay. So here you can see that we have 2 electrons here, and then we have 2 electrons there, so we don't need to do anything. So let's describe the function of the next cell. So here we have electrodes, copper and silver. So when I look at table J, you can see that copper is more active than silver. And as the arrow indicates here, the electrons are going to flow from copper to silver. So I'm going to use this information to help me write in the flow of electrons on the Voltaic cell. So I'm going to start at copper and I'm going to head towards silver. So as we recall, we always start at the anode, and that's the site of oxidation, and the electrons will flow through the wire. And from here, we're going to go towards the silver. So the silver is going to be called the cathode, which we refer to as the fat red cat. So copper is my anode and silver is my cathode. And the electrons are going to flow through the wire in this direction. So in a Voltaic cell, the anode has the same charge as an anion, it's negative, and the cathode has the same charge as a cation, which is positive. And to write the half reactions, for the oxidation half reaction, what we're going to have to do is show an increase in charge. So the 2 species we have on this side are the copper with a 0 charge and the copper with a +2 charge. So in this case, copper atom will become copper +2 ion, and I'm going to have to add the electrons. I need 2 electrons on the most positive side, or the product side. And now for the silver, to write its reduction half reaction, I need to have the charge reduced. So it's going to go from silver ion to the silver atom. And then I have to add the electrons to the most positive side. So I'll place them here. In order to balance this chemical reaction, what we're going to have to do is start with the skeleton reaction, and noticing that we have 2 electrons lost and 1 electron gained. So I'm going to have to multiply my silver by 2. So if I write what's on the reactant or before the arrow first, I see that I have a copper, and over here I have 2 silvers and then here I have 1 copper ion, and over here after the arrow I have 2 silver atoms. So this is my balanced reaction. So from table J, I can see that I start at the anode and I'm going to lose the electrons and they're going to travel in this direction. Now in order to have a complete circuit, if the electrons are flowing in this direction, the negative anion needs to flow back to the anode. So in the salt bridge, the negative charges will flow back to the anode and the positive charges will flow towards the cathode. So we start all cell investigations by looking at reference table J. On reference table J, I can see magnesium is much more active than lead. So we're again comparing magnesium and lead. And so the electrons are going to flow down from magnesium to lead. So I'm going to draw in the electrons through the wire, and then I'll start to label my cell. So we start at the anode. So we know that the anox, and then we'll finish here at the cathode. And so we're starting at the anode, the electrons will move to the cathode. If I wanted to write the half reaction for the anode, it's oxidation, which means the charge goes up. So here, my magnesium atom becomes a magnesium ion, and I'm going to have to add 2 electrons to the most positive side. So these 2 electrons are going to travel through the wire, and they're going to be accepted here. So what's going to happen is the reduction of charge happens in this half cell. So in this case, my lead ion will be reduced to a lead atom. Now I have to add in electrons, and so I always add my electrons to the more positive side. So if I needed to write my balanced reaction, I'll notice that here I'm losing 2 electrons and here I'm gaining 2 electrons. So all I have to do is make sure that the species that are before the arrow are written before the balanced arrow. So I have magnesium and lead ion. And then after the arrow, I have magnesium ion and lead atom. So no coefficients are needed because my electrons are already balanced. So again, how this cell works is as electrons are lost at the negative anode, they will travel through the wire to the positive cathode. Once the electrons arrive here, they're going to reduce these cations, and the anions in the salt bridge will travel back to the anode. And obviously the cations will go towards the cathode. Now I want you to look at this electrochemical cell and see if you can identify the anode and the cathode, write the 2 half reactions, and balance the overall redox reaction. To assist your balancing, I will write the skeleton equation below. So make sure you're using reference table J to find the anode and the cathode, and so you can label all of the parts of this voltaic cell. So hopefully your electrochemical cell looks something like this. Make sure you complete your homework and bring any questions you have to class. I'll see you soon.
Vital to make a battery is this electrochemistry. You take 2 half cells and connect them up so well, with a load to power in between. You need to have electrodes, you see, full of that metallicity. Let electrons flow, across the salt bridge we go, allowing us to make electricity. We start at the anode, electrons are lost there, and go through the wire and through the load on fire. They enter the cathode and reduce the cations, and the anions go through the salt bridge back to where? We start at the anode, electrons are lost there, and go through the wire and through the load on fire. They enter the cathode and reduce the cations, and the anions go through the salt bridge back to where?
Everybody now!
We start at the anode, electrons are lost there, and go through the wire and through the load on fire. They enter the salt bridge back to where?
Where?
We start at the anode. Electrons are lost there and go through the wire and through the load on fire. They enter the cathode and reduce the cations, and the anions go through the salt bridge back to where?
Where?
We start at the anode. Electrons are lost there and go through the wire and through the load on fire. They enter the cathode and reduce the cations, and the anions go through the salt bridge back to where?
Where?
We start at the anode. Electrons are lost there and go through the wire and through the load on fire. They enter the cathode and reduce the cations, and the anions go through the salt bridge back to where?
Where?
We start at the anode. Electrons are lost there and go through the wire and through the load on fire. They enter the cathode and reduce the cations, and the anions go through the salt bridge back to where?
Where?
We start at the anode. Electrons are lost there and go through the wire and through the load on fire. They enter the cathode and reduce the cations, and the anions go through the salt bridge back to where?
Where?